Newton's first law. This is the first of the laws put forward by Isaac Newton, who lived in England in the 1600s. He died in the 1700s. And reading Newton's first law deals with objects and what they will naturally tend to do if something doesn't force them to do otherwise. And this something is a force. Newton's first law can be stated as follows. A body will continue in its state of motion unless acted on by an unbalanced resultant force. By state of motion, we mean its velocity, and that includes, of course, the direction of motion. So if a body is moving, let's say, with a velocity of 5 meters per second in a northerly direction, unless it's compelled to do otherwise, it will simply continue to do that. And the only thing which can compel it to do otherwise is if there's some kind of resultant force. So this introduces the idea of a resultant force. And to explain resultant forces, we need to talk about free body diagrams. So these are free body diagrams. And we often abbreviate that to FBD. So let's go back and let's remember an example which we met earlier on in this course in the section to do with vectors, where we had a ship and that ship was subject to two forces. And we said that those forces were exerted by tugboats, and this force we can call F1 and that force F2. And again, we're not going to worry too much about the size of the forces, simply that there's a ship and it's acted on by two forces. We are looking from above, so you can imagine us in the sky looking down at this ship. The rest of the ship might look like that. And here are the two tugboats, and we've just represented the force which is applied by directed line segments. You can imagine that force to be the tension force. Remember, we talked about different types of forces in the previous section. So that's a tension force, F1 in the rope between the first tug and the ship, and F2 in the rope between the second tug and the ship. We can take this, which is a physical diagram showing the situation, and we can reduce it, i.e. simplify it, into what is called a free body diagram. And for a free body diagram, we represent the object of interest by a dot. And very often we put the mass of the object next to that dot. And then what we do is we draw lines, directed line segments, to represent the forces which act on the body. So there's F1 and there's F2. Now you can imagine that if this ship was actually moving, there'd be some kind of resistive force, the sum of air resistance and friction between the ship and the water, which would be acting in this kind of direction. And so we could draw that in as well. But before we draw that in, let's talk about F1 and F2 in a little bit more detail. F1 and F2 are two separate forces, but we can calculate the resultant. And this resultant is what will influence the acceleration, which is due to F1 and F2. So if we simply ignore the drag force, so let's imagine that there's no frictional forces which are opposing this motion, or alternatively, this ship is just starting to move. So at the moment when it just starts to move, there's no frictional force due to air resistance or resistance between the ship and the water. Then what we can do is we can use what we learned in the last section to find the resultant of F1 and F2. And that resultant, we know, would be in this kind of direction, like that, for example. And that resultant is what will influence the acceleration of the ship. So Newton's first law says that this body, because it's acted on by an unbalanced resultant force, so this resultant force is unbalanced in that it is not zero. So that resultant is not equal to 0 newtons. Because that body is acted on by that resultant force, what will happen is that it will accelerate. Newton's second law, as we'll see in the next section, will tell us about how large that acceleration will be. But before we get to that, let's think in a little more detail about this scenario. We have considered the ship's motion in the horizontal plane. So we're looking from above. This resultant will result in an acceleration which is in the horizontal plane. However, if we were to look from the side of the ship might look like this. In the water. And there are forces which act in the vertical plane. You've got the weight of the ship. And then you've got the upthrust. Which the water exerts on the ship. And these two really should be equal. This arrow might look a little bit longer than this arrow. In fact, I can correct that quickly so that it's more representative. So the weight and the upthrust will be balanced because we know that the upthrust will act for a ship that's built properly in such a manner that it balances the weight. As the weight increases, the upthrust increases. As the weight decreases, the upthrust will also decrease. And we see here that a free body diagram for this situation would be markedly different. That free body diagram would show the ship with this mass, and then you'd have the upthrust here, and the weight acting downwards. And these two, because they are equal, will work out to a resultant force which is equal to 0 newtons. And so in this case, when you consider the vertical forces which are acting on the ship, there isn't an unbalanced resultant force. So Newton's first law tells us that this ship will continue in its state of motion in the vertical plane. And there was no acceleration in the vertical plane. The state of motion in the vertical plane was that the velocity was 0. So it will simply continue to do that. So that's, in brief, Newton's first law. The idea of the free body diagram is critically important. You shouldn't take it for granted when you read a question and the question talks about forces which act on a body. You shouldn't take it for granted that you can easily figure out whether or not that body will accelerate or not. You really need to make sure that you consider carefully whether or not there is a resultant force which is not equal to 0 newtons which acts. And a good way to make that consideration is to sketch very quickly a free body diagram. This is a tactic which is very, very useful when you're answering problems in papers, is that you read the problem or the question and then you reduce it to some kind of diagram. And when you are dealing with forces in Newton's laws, it's often quite straightforward to reduce that question, the words in that question, to a free body diagram. It'll give you a better understanding of the situation, prevent scenarios where you overlook something and then you head off down the wrong path in terms of answering the question. Newton's second law can be stated as follows. If an unbalanced resultant force acts on a body, then that body will accelerate in the direction of the resultant force. The acceleration itself being proportional to the resultant force. So put another way, Newton's second law says, if we have a resultant force which acts on a body, which is not 0 newtons, then that body will either speed up or it will slow down. Whatever it does, speeding up or slowing down, will be in the direction of the resultant force. And that speeding up or slowing down, that acceleration will be proportional. Its size will be proportional to the resultant force. To delve deeper into Newton's second law, we've got the example which you can see in front of you. And that is a very basic example of a car which has got a mass of 800 kilograms. And that car is driving along a road. It's moving at some kind of speed, which we would simply call V. Speed V, and that's in meters per second. is acted on by two forces in the horizontal plane. A driving force, and this comes from the tires of the car, which exert a force on the road and the road pushing forward on the car. So that's the driving force, which we call D, and a drag force, which, because it's a resistive force, we will call it R. And we've got magnitudes for these so that we can use this as a numerical example. The driving force is 3,000 newtons and the resistive force is 1,400 newtons. And we can see straight away here that because the driving force is greater than the resistive force, which is the drag force, we're going to have a resultant force. We can draw a free body diagram for this car as follows. Here we've got the mass of 800 kgs. And to the right, we've got a force which is 3,000 newtons. Okay? And that's D. And to the left, opposing that motion, we've got a force which is R, which is equal to 1,400 newtons. So the resultant force, and very often we'll call this F, is equal to 3,000 minus 1,400, which gives us a resultant force which is 1,600 newtons. And that's to the right. So that's fairly easy, calculating what the resultant force is. Now, what we can do is we can have a look at what the consequence of this resultant force will be. And that comes under Newton's second law. Because Newton's second law can also be stated as an equation. And this really is the most important equation in mechanics and dynamics. And that is, the resultant force acting on a body is equal to the product of the body's mass and the body's acceleration. F is equal to ma. And I'm sure that you've seen this equation before. There isn't very much chance that you haven't in your physics course up until this point here. Now, this equation links the resultant force, and you must remember that F is always equal to the resultant force. It's not just the driving force, and it's not just the drag force. It's the summation of those two, the resultant force. The resultant force is equal to the body's mass multiplied by the body's acceleration. So what we can say in this example is that that resultant force of 1,600 newtons is equal to the body's mass, which is 800 kilograms, multiplied by the body's acceleration, which I'll simply put in as A. Rearranging this equation, we get that A is equal to 1,600 divided by 800. And that's a very simple calculation to complete. That A is equal to 2 meters per second squared. And so what we find is that this car will accelerate with an acceleration of 2 meters per second squared. Every second, its velocity will increase towards the right by 2 meters per second. So if it was initially moving at 10 meters per second, 1 second later it's moving at 12 meters per second, another second later it's moving at 14 meters per second, etc. So here we see the power of Newton's second law, is that if we've got any situation in physics and we can calculate the resultant force acting on the body, then if we know the body's mass, we can calculate the acceleration of the body, which allows us now to look into the future and to determine the speed and the direction of travel of the body at some point in the future. And this is a very, very useful concept. Coming back to this example of the car, we've established that the acceleration of the car is going to be 2 meters per second squared, and that's in the direction which is given by the right-hand direction, in the direction of the driving force, which is the same as the direction of the resultant force. Let's talk for a moment about the drag force. And this drag force is going to be made up predominantly of air resistance. There's going to be other components of the drag force, which is the forces of friction which act on the car, other small forces of friction, but really the big addition to the drag force is air resistance. Now, air resistance is a force which you often meet in physics. And air resistance occurs because any body which is moving through the air, so if we've got a body with a velocity v and is moving through air, is going to be pushing aside air molecules, and those air molecules will exert a drag force on that body. And the nature of air resistance is that air resistance opposes the direction of motion. So if this body is moving towards the right, air resistance will be towards the left. If it is moving up, air resistance will be downwards. And air resistance, the force due to air resistance grows as that body increases the speed. In fact, the force due to air resistance will be related to speed by a square factor. So if the speed doubles, the force due to air resistance will increase by a factor of 4. The force due to air resistance is also larger when a body has got a larger cross-sectional area which is facing the air which is moving through. And so in order to reduce the force due to air resistance, you'll find that many objects are created with a streamline shape. A streamline shape is this kind of teardrop shape, and you'll see that this kind of teardrop shape is associated with aeroplanes, it's associated with anything which is meant to move fast through the air. Okay, that kind of shape reduces the cross-sectional area which is facing the air in the direction that the object is moving, and so reduces the force due to air resistance. It's important to understand air resistance and how it works because it comes up so often when we are dealing with problems in physics. Now, coming back to this car, we're going to use the example and what we have established so far to have a closer look at what mass is. Before your study of physics, you probably thought that mass was a measure simply of the amount of material which is in a body. So a body which has got a mass of, let's say, 10 kgs has got twice as much material as a body which has got a mass of 5 kgs. And that's a pretty convenient way of thinking about mass. But I think we need to complicate it a little bit more now that we are at this stage in physics and get a little bit more detail. And really what we want to do is we want to think about mass in terms of Newton's second law, which tells us that F is equal to ma. And mass is the constant of proportionality between the resultant force and the acceleration. You notice that mass comes in and this proportionality sign goes from a proportionality sign into an equal sign. So mass is the constant of proportionality in the relationship between the resultant force and a body's acceleration. So what we have is that if mass increases for a constant resultant force, then acceleration must decrease. So we've got this relationship between mass and the acceleration of a body for any resultant force. Let's go back to this example where we've got our car and we know that the resultant force acting on that car was 3,000 minus 1,400, which gave us a resultant force of 1,600 newtons. I'm going to put this up here, 1,600 newtons, which is going to be in this direction. That is the resultant force. Now let's imagine that the mass of the car, instead of being 800 kgs, was twice that, 1,600 kgs. What would the acceleration work out to? Well, we know that the acceleration would still be obtained by applying Newton's second law in the equation form. So resultant force F would still equal to m multiplied by a. In this case, the resultant force would still be 1,600 newtons towards the right, and that would equal to the mass 1,600 kgs multiplied by the acceleration. And straight away you can see that the acceleration would be equal to 1 meter per second squared, and that would still be in the right hand direction. We see that our acceleration has gone from 2 meters per second squared when our mass was 800 kgs to 1 meter per second squared when our mass is 1,600 kgs. So doubling the mass has halved the acceleration. So again, we come back to this whole thing that there's a relationship between the mass and the acceleration of a body for a given resultant force. At this stage, we're going to introduce the idea of inertia. And inertia is a concept of physics which tries to measure the property of a body which resists changes to its state of motion. And we say that mass is a measure of inertia. So inertia is the property of a body which resists changes to that body's state of motion, and mass is a measure of inertia. Let's put that into a simple everyday example. Let's say you have got a small compact vehicle. You're thinking of the kind of vehicle which is a sedan or a small hatchback, which is 2 doors. Typically, that kind of vehicle would have a mass of about 800 kilograms, like we have with our car that we have in our example. If you park that vehicle on a slight gradient, a slight incline, and you forgot to pull up the parking brake, or what in some parts of the world they call the handbrake, and then that vehicle started to slowly roll down that gentle incline, you might jump behind the vehicle and try and stop it rolling. That's not a good idea, but you might do that. And you'd be probably successful, because the vehicle, as it starts to roll, it doesn't have that much inertia because it's got a low mass. Remember, mass is a measure of inertia. So if it's starting to roll and it's got a low speed, to change its state of motion, which is it moving at that low speed, is not too difficult. So the inertia of that compact vehicle is low. Let's say we had a lorry which had a mass of 8 tons. And that lorry started to roll down that same incline at the same slow speed. You would never try and jump behind that lorry and stop it, because although it is moving at a low speed, it has got great inertia. It's got a large amount of that property which resists changes to its state of motion. So when you try and change its state of motion from rolling down the incline at a low speed to being stationary, the inertia, because it is great, will not allow you to do that. You have to exert a very, very large force, which is why trucks will have assisted brakes, power assisted brakes. Because when a truck is moving at any speed, it is more difficult to stop than a compact vehicle, passenger vehicle, compact family vehicle, which is moving at the same speed. So inertia is measured by mass. And inertia is the property of a body which resists changes to its state of motion. So what Newton's second law does is it links resultant force, a body's mass, which is a measure of its inertia, and the body's acceleration. So the effect of a resultant force is determined by the size of the body's mass. A resultant force will cause a certain acceleration for a body with a certain mass. If that mass is increased, the same resultant force will lead to a lower acceleration. On the 15th of October 1997, Andy Green was at the controls of a land vehicle powered by 2 jet engines called Thrust SSC, and he set the world land speed record. In fact, he bettered a record which had been set by the same vehicle piloted by him about a month earlier. And that speed record is now at 1,227 kilometers per hour, equivalent to 763 miles per hour. And that is above the speed of sound. That record stands till today. And this is speaking from the time position of the end of 2019. And I think it will stand for a little while longer. It's a very good example for us to look at if we're considering forces, Newton's laws, and how objects can go faster, and how, as objects move faster, the effect of air resistance becomes greater, and the difficulties in setting new land speed records, and in fact air speed records as well. So here we've got thrust SSC. I've drawn it. You can have a look on the internet to see better pictures of it. There are a couple of really good videos which are on the internet which you can watch, which talk about how thrust SSE came to being and talk about the day when they set the world land speed record. And I really encourage you to have a look at them just for added interest. But for the purposes of this course, we're going to consider a free body diagram of thrust SSC. And we're just going to put its mass down there. There's going to be a forward force, which is going to be the thrust produced by the two jet engines which power the vehicle. And then, of course, in the backwards direction, what you have is really air resistance. And we're going to call this R, and we're going to call the thrust T. There will be a few other forces which contribute to a backward force, but the major force is air resistance. So on that day, on the 15th of October, Andy Green accelerated the vehicle through low speeds quite carefully, because he had to be careful not to let any of the desert dust, because they were doing this in a desert in the United States, let any of that dust get into the air intakes. And slowly he managed to bring that vehicle up to the region of 100 miles per hour, 200 miles per hour, continuing that way. And what he was doing through this process is he was increasing the thrust which acted on the vehicle, which naturally would accelerate the vehicle. And at one point in that acceleration, the acceleration was 25 miles per hour every second. So it's quite a great acceleration. And as the vehicle accelerated and increased its velocity in the forward direction, the force due to air resistance increased. And you remember from the previous section that I'd mentioned that the force due to air resistance, it increases according to a square relationship with velocity. So as speed was doubled from, let's say, 100 miles per hour to 200 miles per hour, the force due to air resistance actually increased by a factor of 4. And herein is a big limiting factor to how fast you can go when trying to get to a top speed. Because the faster a vehicle goes, the larger the force due to air resistance. So the larger the additional driving force you have to apply to accelerate that vehicle further. And so in this case, as the thrust was increased, the force due to air resistance would increase. And if the thrust is held constant at a particular value, acceleration, while it will be positive, so the vehicle will continue to speed up, will become smaller and smaller, because as that vehicle accelerates and its velocity in the forward direction increases, so the force due to air resistance will increase until eventually the force due to air resistance matches the thrust. And if you think of a falling object, this is exactly what happens, which leads to terminal velocity, which we'll cover in another example. But in this case, what happened is that Andy Green was able to increase the thrust sufficiently to maintain an acceleration to take him to a speed in thrust SSC, which was just above the speed of sound, and so set the world land speed record in October of 1997. This is a short note about coordinate systems. Coordinate systems, generally, are a way of using numbers to uniquely locate points in space. And in physics, because we often deal with position, direction, we use coordinate systems quite a bit. In terms of dynamics, what we've been dealing with, and vectors, coordinate systems are very useful in establishing the direction of resultant forces, or the direction of other vectors like accelerations or velocities. Let's explain it using this simple example of a rocket, which is subject to forces 40 kilonewtons in the upward direction, 60 kilonewtons downwards, and that 60 kilonewtons might be the weight of the rocket, and we could also account for air resistance in that 60 kilonewtons. So let's say the 60 kilonewtons is a sum of the air resistance and the weight of the rocket. So it's a sum of all of the downward forces. What we have is a simple scenario which can be represented by the free body diagram as follows. So you've got 60 kilonewtons, and then upwards you've got 40 kilonewtons. Okay? And up until now, I've been using the words upwards and downwards, but what I could do is I could define a positive direction. So I could put an arrow going up and say that that is positive, which would then make the 40 kilonewton force a positive force and the 60 kilonewton force a negative force. The usefulness of this is when I'm calculating the resultant force, all I need to do is sum up the forces. So that resultant force is simply equal to a summation of all of the forces. And that is equal to 40,000 plus minus 60,000. Because remember, the 60 kilonewton force is in the negative direction, which will give us a resultant which is 40,000 minus 60,000, because plus minus 60,000 gives us minus 60,000, which will give us a result which is minus 20 kilonewtons. Okay, that's fairly straightforward. The value of it is that this negative sign tells us that the 20 kilonewton resultant force is in the negative direction, which is downwards. So what we would expect is that the resultant force being downwards, if this rocket is moving upwards, we will have a deceleration. And when we calculate the acceleration should come out as negative, which would represent a deceleration. And we can do that. The acceleration is equal to the resultant force divided by the mass, which would be the resultant force of minus 20,000 newtons divided by the mass, which is 2,000 newtons. And so what we have is that this would work out to an answer of minus 10 meters per second squared, which tells us that the acceleration will be 10 meters per second squared in the negative direction. So if this rocket is moving up, which is in the positive direction, and the acceleration is down, which is the negative direction, we know that it is decelerating. It is slowing down. This use of a coordinate system is very, very handy when we come upon complicated problems in physics, and we want to know the meaning of the answer that we get. So let's keep that in mind. We mentioned tension right at the beginning of our discussion on forces as being a contact force. Tension exists whenever a rope or a chain is attached between two bodies typically, and a force is applied which is transmitted through that rope or that chain or that cable, whatever it might be. And tension, an understanding of it, is useful because we often see these kinds of situations where there's a rope or a chain attached to something in everyday life. So if we think about using a rope to raise a sail on a yacht, or for example, using a rope in a pulley system, or using a chain or a rope to hold up a structure like a tent, for example, when you're camping, all of those are situations where a tension exists in a cable of some sort, and we may need to work out what the value of forces and the effect of those forces would be. So in this particular example, we are told the following. A can of paint with a mass of 6 kilograms hangs from a rope. If the can is pulled up to a rooftop at a constant velocity of 1 meter per second, what must the tension in the rope be? A good tactic is straight away to draw a free body diagram for this can. And that free body diagram would be as follows. So we've got a can there, and it has got a mass of 6 kgs, and it has got a weight. Okay, and there's a tension, which is the upward force. So that's the tension, and that's the weight. The physical diagram for this can would look something like this. So that's the can, and here's the rope, and the rope would be pulling upwards, using the tension in the rope, and the weight would be acting downwards. So this would be the weight and this would be the tension. That is represented as this free body diagram, which captures the essential elements of the question and allows us to understand the question better. So in this case, we would like to know what the tension must be. So we want to know what the tension is. We know the value of the weight. This weight is given by m times g, which is equal to 6 multiplied by, and in this case we'll take g to be 10. If you are unsure about how I did that calculation, then just refer to any section in the physics textbooks which will explain how we calculate weight, and that weight works out to 6 times 10, which is 60 newtons. Now we would like to know what the tension is. If we go back to the question, we are told that this can is moving upwards with a constant velocity. There it is, constant velocity of 1 meter per second. Now, in fact, the 1 meter per second is not that important to us. What's really important to us is that it's a constant velocity. Because a constant velocity means that there is no acceleration. And we know from Newton's first law that if we have got no acceleration, then it must follow that there is no resultant force. And for there to be no resultant force in this situation, looking at the free body diagram here, then our weight must equal to our tension. So straight away, we can say that this tension must equal to 60 newtons. And there wasn't very much calculation to get to that. So we can get to the solution of this without doing very much calculation at all. But let's change this example slightly. Let us say that instead of moving upwards at a constant velocity, what if we wanted this can to move upwards with an acceleration of 1 meter per second squared? So what if the acceleration was 1 meter per second squared? What would the tension need to be in this case? And we can come back to our free body diagram. The tension is no longer 60 newtons, clearly. But our weight, we know, is 60 newtons, which acts downwards. But we need some kind of resultant force in the upward direction in order for us to have an acceleration of 1 meter per second squared. So what we can say is from Newton's second law, the resultant force is equal to the body's mass multiplied by its acceleration. We want to know what this resultant force would be, so that is still an unknown, which is F, must equal to the body's mass, which is 6 kilograms, multiplied by the acceleration, which is equal to 1 meter per second squared. So our resultant force must equal to 6 newtons. Now, if we have got a downward force of 60 newtons and our resultant force must equal to 6 newtons, then we know that our tension must equal to greater than 60 newtons by 6 newtons. So our tension would naturally work out to 66 newtons. So when we say our tension minus our weight, we get an answer which would be equal to 6 newtons. And that will lead to our acceleration of 1 meter per second squared. Just take a moment, maybe roll back in the video and play that back to yourself just to make sure that you are okay with that calculation for both cases, when the can was moving upwards with a constant velocity of 1 meter per second, and when the can was accelerating upwards with an acceleration of 1 meter per second squared.